Okay. Welcome everyone to the 80th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Michal Hrbek from the Czech Academy of Sciences in Prague, and he'll be talking to us about topological derived Morita theory and some applications.
Thank you for inviting me to speak here. It's a big pleasure. So my topic today will certainly be about triangulated categories. It will not be about group theory, or at least the applications are not there yet. So let me start with the outline. I will start with some remarks of historical or also rather recent nature about tilting theory and derived Morita theory, and these will be neither comprehensive, so I will sort of cherry pick a part of the history as it happened, which will fit my narrative, and it will actually also not be chronological. I will, although I will give the dates, I will sort of choose a way of narrating the story which will fit me. Then in the second part, I will talk about the main result of this arXiv paper as is written in here. And that is an attempt to build a Morita theory, derived Morita theory for large tilting complexes, which will involve topological algebra in the sense of Leonid Positselski. So the keyword here is contramodule over a linear topological ring. And if time permits, in the last section, I will talk about some of the results of this newer preprint from this year with Lorenzo Martini, where we apply this topologically flavored Morita theory. First, there will be some general results about finiteness conditions of hearts of certainty structures, where we really make use of the contramodule machinery. And finally, this will be applied in a specific setting of commutative algebra. So commutative algebra is not the usual settings when one would suspect tilting theory to work, but that's precisely what one gets passing from the classical setting to this setting of large tilting complexes. There are more areas where these are ubiquitous. Okay, so let me start with tilting theory past and present. And as I said, I do not start chronologically. I will actually start with some pretty new take on tilting theory, and very general one for that. So the generality here is triangulated category with coproducts. This is not the only setting in which this works. Actually, one can, the similar definition will work also in the setting of small triangulated categories. And actually then for the results I have in mind, one actually have to assume more than is written here and to work in compactly generated triangulated category. But okay, at least for this slide, this assumption will make everything work. Bit of notation. So given an object T in this triangulated category T, we will consider these orthogonal categories, orthogonal with respect to just one direction according to the shift. So this is the category obtained by taking positive orthogonal to the object T. So it consists of all those objects X, such that there is no morphism from T to some positive shift of that object. So in other words, we are looking at all objects which have no positive extension by T, right? And similarly, we have this non-positive orthogonal. So this time we will look at the orthogonality condition with respect to non-positive shifts. And I will also use some variation, so maybe this inequality can be strict and so on. This, I hope, will be clear what this meant. So the definition, a very general definition of a tilting object, that is something like a candidate to be tilting, which is found in these two independent works from similar time frame. One is Psarodakis Theoria, the other one is Nikolasa or Zvonareva. So here an object T in the triangulated category is called tilting, a tilting object, and the definition is very, very compact. We want this pair of orthogonal categories to form a T structure. So some comments about that. First, the second constituent, which is called the coil. Actually, when one attempts to generate a T structure by an object, then this is a very natural thing to do. We look at all things which are non-positively orthogonal to T. And actually, under multi-assumptions on the ambient category, it's always possible to have a T structure where the second constituent looks like this. The most general result is a recent paper by Niemann, so it's enough to assume that T is well generated. And this works. So this definition is more about the special form of the isle, of the first constituent of the T structure. So it's very special that all objects in the isle are positively orthogonal to T, and that's the main part of the definition of a silting object. So this is a very compact definition which holds in many cases. As a consequence of the definition, we recover some more usual properties which one would expect from a tilting object. So generally speaking, a tilting object or a silting object should encapsulate some properties which are enjoyed by projective generator in an abelian category, and sort of transfer them to triangulated setting. And this is what happens here. So consequence of this definition is that first, T is a generator. So it is a weak generator of the triangulated category. So that's something like a generator of abelian category. And secondly, we have this orthogonality condition. So there are no self-extensions of T, and this formulation is actually stronger. So this category at T, the additive closure of T, consists of all coproducts of copies of T and their retracts. And so this condition says that there is no extension of any coproduct of copies of T by T in the positive direction. And actually, under some assumptions, this implication could be replaced by an equivalence. This is not known in all cases, but for example, if the triangulated category is a derived category of a ring, and we further assume that T is a bounded complex of projectives, then it is known that these two conditions actually characterize this situation. But for general triangulated categories, this definition works and gives a meaningful theory. Okay. What is a tilting object? This is actually the object of interest if we are about to build something like a Morita theory. So T is tilting if in addition we get this negative orthogonality condition. So this category of this additive closure of T actually is also negatively orthogonal to T. Equivalently, this says that this additive closure of T lives in the heart of this T structure, of the tilting T structure. And okay, now comes the sort of philosophy / meta theorem. So what are these tilting objects expected to do? A tilting object, if it exists in the triangulated category, is expected to give rise to a triangle equivalence. That's what tilting theory was developed for, finding some derived equivalences. And the derived equivalences should be between T and derived category of the tilting heart. That's the heart of the tilting T structure, which equivalently could be written as the orthogonal to T with respect to all non-zero degrees. And this heart is an abelian category. And in this settings, it's actually a co-complete abelian category with projective generator. The projective generator is the T itself living in the heart. So this is a sort of expectation / meta theorem, and it becomes a theorem in many situations. So in particular, so how does it work in general? So usually one gives some restriction of what the triangulated category is. Usually everything works well if the category is a derived category of a ring, or maybe something a bit more general. Be it of small or large kind, generally speaking. Then one maybe gives some extra condition of what T should satisfy. Maybe it should satisfy some homological bound. In general, everything's work really well if T is compact, but in this lecture we want to be a bit more general than that. And then in the end, it's necessary to specify what kind of derived category are we looking at. So maybe it's the perfect derived category in the small setting. Maybe it's the bounded or unbounded derived category. And recently it seems that for certain settings, it's actually better to pass to some exotic kind of derived categories, but this will not be the topic today. So this is the very general take on silting and tilting objects and what they are expected to do. Okay, I will also need to invoke the dual settings, which is also found in these two works. So essentially everything dualizes. So we have a triangulated category with products. We look at these two orthogonal categories now to the left. So we look at the left orthogonal categories. An object is called co-silting if the dual condition holds. So the object co-generates a T structure of a special form in this case. So of course, in triangulated categories arising in nature, co-generating a T structure is usually the harder thing to have, but sometimes it works nicely. Then we get the special condition, which sometimes characterize the definition. C is a weak co-generator of T. and we get this self-orthogonality condition. Now we have this productive closure here. So this is the category of all retracts of our products of copies of C. We have the cotilting object, which in addition satisfies the negative orthogonality condition. And then again, there's this philosophy statement. So cotilting objects are again expected to give rise to triangle equivalences between T and derived category. This time the derived category, the cotilting heart, has the dual property. So it's a complete abelian category with injective cogenerator. So this is the very general tilting theoretic setting. So one case, one situation in which it works very nicely, and we get something more tangible. The derived category of an arbitrary associative unital ring. So this is the unbounded derived category of right R modules.
Michal?
Yes.
Hi. There is a black thing over the title. What about of the title of the slides?
Okay. I should move this. Okay. Is it better?
Yeah, no, it's better. Thank you.
Okay. Very good. Right. So actually, most of the results of today will be about this category. Then the whole theory works better if we also put a mild restriction on the tilting object. So we have the tilting object in this triangulated category. From the definition is from the past slide, and we will actually rename it to a tilting complex if one extra condition holds, and that is if the object is isomorphic to a bounded complex of projectives. There is no size limitation of the projective, mind here. So the projectives can be big, but the complex is a bounded complex of projectives. So it is sort of homologically limited from both sides. And then we also get the notion of tilting complexes if it satisfies the negative self-orthogonality condition. And then we really get a result, not just a meta-theorem, but a theorem. So these tilting complexes of right R modules, they parametrize a set of derived equivalences. So which derived equivalences are there? These are derived equivalences between the module category on one side and a category which has the properties, the same properties as the tilting heart. So this is a co-complete abelian category with a projective generator. So, okay, I put a one-to-one correspondence a bit more precisely. What does this say? So this is composed of two statements. So given a tilting complex, and this is in this paper, Pseudodakis Virtoria, it gives rise to derived equivalence to the heart. I've put a bounded derived equivalence of possibly large objects here, which makes this statement true, but in this direction also the unbounded derived equivalence will exist. And from the other side, given such a derived equivalence, what this direction says that there is a tilting complex whose heart is equivalent to H. So we get this nice theory. We get that these objects essentially govern the derived equivalences between the module category and this special set of, or special class of abelian categories. And we also get a dual statement. And there are some remarks I should comment here, otherwise it's just dual. So first, this is something which will make my life easier. So the cotilting setting in the setting of derived category of a ring will be on the left. So for me, tilting object lives on the right of the ring, right R modules. The cotilting and cotilting stuff will live on the left. And the reason will become clear soon, I hope. Then a cotilting object will be renamed to cotilting complex if it is, in addition, isomorphic to bounded complex of injectives. So we get this sort of dual homological limit. And then something good happens here. So these cotilting complexes parametrize, and we could put here the dual notion, so complete categories with injective cogenerator, and this would be true. But actually in this setting, these hearts are special. They become actually Grothendieck categories. So automatically the direct limits in these categories are exact. So that's something specific to this setting. So this statement is maybe a bit more natural. What we are doing, we are parametrizing derived equivalence between module category and some Grothendieck category. Okay, so this is the still pretty general tilting theory for a ring. Now we skip in history some time back to much more classical setting. So this is the derived Morita theory for rings of Rickard. So this theory essentially fully describes what happens if two rings are derived equivalent, if two derived module categories over a ring are equivalent, or triangle equivalent to be more precise. So given two rings, the following is equivalent. There is a triangle equivalence between the derived categories. Again, I've put the bounded derived categories of possible large objects, but the statement remains true if we go to unbounded settings, also if we restrict to the perfect derived categories here. And this is all, the situation is encaptured by the existence of a special tilting complex, a tilting complex which is compact, meaning that the covariant home factor defined on it commutes with coproducts. So in Rickard's work and many other work, this is called just tilting complex, but I will distinguish it from the large setting by calling these compact tilting complexes. So this is a compact tilting complex of right R modules, and the connection is with S is that its endomorphism ring is isomorphic to S. And actually, so if we are in this situation, we get something a bit more. We get some nice symmetry. So and also we get a representation of the derived equivalences. So there is this picture, and I will sort of explain what it means. So we get this derived equivalence, which is here in this point 1 between right R modules and right S modules. And this is actually, one can actually represent this derived equivalence by this R home factor based on T. Then we also get, somehow for free, we get this the picture on the left. So this derived equivalence is left-right symmetric. We get also derived equivalence of left modules between R and S, and this is represented by the derived tensor from T. The reason for that is that we have the equivalence between compact objects on the left and right of R. So from a compact tilting object on the right, we get also a compact tilting object on the left. And furthermore, it is not hard to convince ourselves that this pair of derived equivalences is compatible with the tensor structure. So we have the derived tensor structure over R and the derived tensor structure over S. And these two are compatible with the two equivalences via commuting of the square. So this is not too hard to see actually, but sort of this picture, I will have an analogy later for that in the more general setting. So once we pass to the topological Morita theory, which I aim to explain, we will get a similar picture, which will be less symmetric and also somehow less trivial to obtain. And the compatibility with the tensor structures. And also, okay, to connect this with the previous slide. So what is the connection? So the tilting heart is equivalent to the module category of rest, the category of right modules. And also we can bring in the cotilting picture if we want sort of forcefully here. So also the category of left S module is equivalent to the cotilting heart. And what is the cotilting heart? Where do we get it? So there is actually a dual cotilting object to T, and the duality is this character duality. So we dualize over the integers with respect to this injective cogenerator of abelian groups of Z modules. And what we actually get is a cotilting complex of left R modules, and its heart is the category of left S modules. So this is a Grothendieck category because it's a module category, and this is a category with projective generator because it's a module category. And this will become less symmetric once we pass to large tilting theory.
Could I ask you a question?
Of course.
I'm Peter Webb.
Hello.
Hi. Could you maybe just elucidate a little bit the difference between a compact tilting complex and a tilting complex as you did it before? So a tilting complex was a tilting complex isomorphic to a bounded complex of projectives. And the complex, so is the difference with a compact tilting complex that those projectives must be finitely generated? What is the difference between saying it's compact?
It's precisely what you just described. So in the derived category of a ring, the compacts are bounded up to quasi-isomorphism. These are bounded complexes of small projectives.
Okay,
yes.
Okay, so the difference is the finitely generated. Thank you, thanks.
Yes, precisely that. Thank you. That's precisely the difference, that in this setting, the projectives are finitely generated, whereas in the general situation, we allow them to be large. Precisely, okay. Yes. Okay, so this is the compact tilting complex setting, the classical one. Now, after this result in the 90s and zeros and tens, the large tilting theory emerged. So the theory of large tilting modules and large tilting complexes, and a lot of aspects of the theory, although they were theoretically considerably harder to achieve, worked well. But the question sort of remained in various forms, and that is there a Morita theory behind these large tilting objects? And I will now, as I said, I'm sort of cherry picking some of the results. The story is a bit larger. But so let me now restrict to the setting of tilting modules, because for these objects there's a bit more in the literature. So what is a tilting module? Tilting module is a tilting complex which also happens to be a module. So it lives just in 1 degree. And S will again denote its endomorphism ring. Then unless T is compact, then actually one cannot expect the Rickard's theory to work. So R and S will not be derived equivalent, and I will give a bit more precise meaning to this bullet point in a second. However, so now I'm describing the work of Silvana Bazzoni. There is a definition which one can apply, which makes the situation a bit nicer. So we say that T, the tilting module, is good if, and there's a technical condition, if the ring itself can be finitely co-resolved by finite coproducts of T. This condition has a nice interpretation. So what this actually turns out to be equivalent to, this T is not compact over R, but this condition ensures that it is compact over its endomorphism ring. So that's what happens here. And this condition is mild in a certain sense. So you can, it can fail in general, but you can always replace a tilting module by another one, which is equivalent in a sense, which is good. So equivalent here means that we obtain the same T structure. And in fact, it is enough to replace T by a coproduct of copies, by a suitable coproduct of copies to achieve this goodness condition. So this is a mild condition which can always be achieved by mildly sort of poking into the tilting module. And then what we get is the following. So this is a result of Silvana Bazzoni, and then in the generality by Bazzoni, Mantese, and Tonolo, and says the following. So in this situation with the good but possibly large tilting module and its endomorphism ring, we have again this Aron functor, which goes from the derived category of R to derived category over S. And this time it is not an equivalence, but this good condition ensures that this is fully faithful. So we get an embedding. And in fact, what they also prove is this embedding is an equivalence if and only if T is compact. So we get that. The natural question now is the following: can we describe the image of this embedding? And hopefully can we describe it in algebraic terms, leading to a Morita theory? So that is the question which was there, and a breakthrough came recently in the form of topological algebra, or at least particular flavor of topological algebra. So let me explain that. This will be a sort of 2-slide crash course on the theory of contramodules. So what is the basic object in this flavor of topological algebra? It is a topological ring, R, and this is a left linear topological ring. So what is that? It is a topological ring in particular, so a ring with topology which is compatible with the ring operations. And the linear, or left linear to be more precise, here means that we have a base of neighborhoods of the 0 point, which is formed by open left ideals. So in other words, there is enough open left ideals in the topology that they determine the topology fully. We can just look at those left ideals which are open, and we know everything about the topology. Attached to such a creature comes an abelian category. So we can consider the category of left discrete R modules. So this is a category which sort of captures the topology. And it is defined in relatively simple terms. So it is a full subcategory of ordinary left modules. And it consists of those modules whose elements are annihilated by open left ideals. So for each element of such a module, there is an open ideal which annihilates that element. In other words, maybe more algebraic terms, this is a category of torsion modules with respect to the topology. More precisely, this is a hereditary pre-torsion class inside this category of modules. This is a fairly commonly appearing structure, certainly popular in algebra in areas such as study of ring epimorphism or theory of torsion classes. It also appears in different areas under different names. So there is a theory of smooth modules over Lie algebras, which by considering the enveloping algebra actually fits with this. So smooth module would be another name for this creature. And this is always a Grothendieck category. Now the question is there a different structure on the right of such a topological ring. So is there an abelian category of right modules which captures the topology? And there is a good intuition for that. So this was a category of discrete/torsion/smooth modules, but we can also consider complete modules which are complete with respect to induced topology. And these make sense to consider on the right. So for each right module over this topological ring, there is induced topology of abelian subgroups. We look at these subgroups of these forms. So these are not right submodules, but these are subgroups. And we can consider the inverse limit of these. And the inverse limit actually becomes a right R module. And there is a natural map of modules from M to this, what one would call a completion. And we will say that M is complete if this map is an isomorphism. So there is a notion of complete right module. At this point, it will be good to assume that the ring itself is complete in the same definition. So this is not a big assumption. If the ring is not complete, then we can pass to its completion by the similar recipient, and that will be a complete ring. The problem is with this sort of naive notion. So certainly the category of complete modules has been considered in different settings, but the problem, at least from algebraic point of view, is that it is not well behaved. In particular, it is almost never abelian. It fails to be abelian. And the solution is precisely what Positselski theory of contramodules aims to do. The solution is in enlarging the category so that it is abelian and enlarging it in some controllable way so that it is defined algebraically and has hopefully nice properties. So there is a right module counterpart to the category of left discrete R modules developed by Positselski. And so where it comes from, the name contramodule actually comes from an old work from the 60s of Eilenberg and Moore. So they considered, this is actually the work where they defined what a commodule over a coalgebra is, which became a rather popular notion. And they also defined what a contramodule over a coalgebra is, which was almost forgotten for something like 40 years. There are maybe two or three references throughout the time. And so what Positselski did in something like 2008-9 was to sort of resurrect this notion and generalize it to this setting, which actually found many applications. So what is a contramodule? A contramodule is defined in similar terms as a module is, at least in one way. So we actually define some set of linear combinations on a group, and this will be the structure. So a right contramodule is an abelian group together with the notion of linear of infinite summation. So it is a linear operation of infinite summation. So apart from the finite finite linear combination is what I mean to say. We allow some infinite linear combinations to be computed in a linear manner. So we are allowed to compute those linear combinations of elements of M by scalars from the topological ring, which satisfy this condition. They converge to zero in the topology. So what does it mean to be converging to zero? It means that for each open left ideal, all but finitely many of these scalars belong to that ideal. So in other words, the linear combination becomes finite modulo each left open ideal of the topology. In particular, if we start with a complete right module, then we have a natural way to defining infinite summation. So starting with a complete module, we can look at these quotients from the last slides. And in each of these quotients, the linear combination becomes finite. And then we can define what the infinite sum is using this inverse limit presentation. So for complete modules, this sort of recovers this natural way how to compute infinite sums. But the point is that this abstract definition will also yield, almost always, it will yield examples where it works, but it is not obtained by completeness. So this is an abstract definition of this infinite summation, and there are some axioms, which I will not write here. So what do we obtain? We obtain the category of contramodules. The maps are maps preserving these infinite linear combinations. And this is an abelian category. And in fact, it is a co-complete abelian category with a projective generator. The projective generator, I will explain in a bit, is the topological ring itself. So we get something which already looks like that tilting heart, right? Some more properties.
There's a question in the chat. Can you
yes.
Michal Hrbek asks, are all these sums countable?
Not necessarily. By definition, not necessarily. They can be of arbitrarily large size. Yes. Okay. So there is a forgettable functor from contramodules to ordinary modules. We just forget the infinite sums and keep the finite ones. But unlike for the discrete modules, which were a full subcategory of ordinary modules, this functor can easily fail to be fully faithful. In fact, it can fail to be full. That's the part which it can fail. So that's one thing which makes the theory a bit maybe that's one aspect which makes it tough sometimes. Another one, so this functor preserves products, but often it does not preserve coproducts. And in fact, so there is this category is co-complete, but very often the coproducts are not exact. So something more specific. So some example of computation of what a contramodule can look like over a topological ring. So for any set, this is what the coproduct of copies of the ring itself looks like. Yeah? So if we take the topological ring itself, it is complete, so it has a contramodule structure, and the coproduct of copies of R, of X copies in R in this category looks like this. So this is a subgroup of the ordinary product, but it is a bit larger than the ordinary module theoretic coproduct. It contains all these sequences which again converge to 0. And this is the coproduct in the contramodule category, and well, the ring itself is the projective generator. So that's some aspects of the structure. There's a bit more. There are some similarities to module theory. We have this pairing between the category of right contramodules and left discrete modules called the contratensor product. So this is a nice additive bifunctor commuting with coproducts in both those categories. And it satisfies, and is actually determined by the adjunction formula one would again expect from module theory. So this Homin groups from this contratensor product to some abelian group is naturally isomorphic to contramodule theoretic Hom between this contramodule and this dualization of this discrete module with respect to the group. This again has a contramodule structure, a unique contramodule structure. So that's another nice aspect which sometimes allows to do module theoretic-esque tricks in this setting. Quick example, consider the ring of p-adic integers. Yeah, this is a complete linear ring. The topology is the p-adic topology. So what is the category of discrete modules? This is not very surprising. This is the category of p-torsion abelian groups, which is the same as p-torsion modules over this ring. And what is the category of contramodules? This is slightly less usual. And this happens to be equivalent to the category of reduced cotorsion p-local abelian groups. So these contain all of the p-adically complete groups, but also some other groups. Okay. So now I said that this theory has applications, and there's one application which is relevant to my lecture, but also it's connected to some very classical results from module theory and representation theory in particular. So the following is classical. It goes back at least to 60s. Given a finitely generated module and its endomorphism ring, this additive closure, so again, this is the category of coproducts of copies of M and their retracts, is equivalent to the category of projective right modules over the endomorphism ring. And the equivalence is given by this covariant Hom functor. And so this is classical, but it's also a very useful thing. So this additive closure of M, this encaptures many decomposition problems of the module M, and it has been a very successful strategy to translate decompositions problems in representation theory to projectives over the endomorphism ring. If one is lucky, maybe this endomorphism ring is special, and then there are some ring and module theoretic results about the structure of projectives. And the question is, what if M is not finitely generated? Then this result almost always fails, because usually this Hom functor does not commute with coproducts of modules, and then this cannot be true. And the solution to this is to endow the endomorphism ring with a topology. And this, again, is an idea which has been around for some time. So this endomorphism ring is a topological ring, endowed with what is called the finite topology, which is defined in the following way. So the basis of open left ideals is indexed by finitely generated submodules of M. And so the corresponding ideal consists of all those endomorphisms which kill that finitely generated submodule. So this is a nice topology, and it turns out that the contramodule machinery fits here into the puzzle absolutely perfectly. So this is a result from a recent paper of Positselski and Šťovíček, where they show that for a module and its endomorphism ring endowed with this topology, the ring is actually complete. That's not so difficult to convince one about. And then we get a similar result with contramodules replacing modules. So this additive closure is equivalent to the category of projective contramodules over S.
I have a question
Yes.
regarding this result by Jan and Leonid. So R doesn't have to satisfy any conditions?
Sorry, come again. R doesn't have to
satisfy any conditions?
No, this is for a general ring, and actually it works a bit more generally. So it works over rings with many objects. So unitality of the ring is necessary here, and it can be formulated in special. For example, I think it works in finitely presentable Grothendieck category. So this actually can be even more general than I've put it here.
Okay, thank you.
Okay, and in that same paper they actually applied it to the tilting setting, answering the question about the image of the inclusion of derived category of R into that derived category of endomorphism ring. So let me explain that. So now we are so this T is now a special module. It is a tilting module, but without any assumption on its size. And again, this is the.
There's a question in the chat. Can you have a look, please?
Yeah. Okay. Yes. Let me see. Chat. Is it true since coproducts? Yes. Yes. That is true. Yes. So the functor does not commute with coproducts, but that's precisely so the coproducts in the contramodule category are precisely the ones that fit this setting. So those are precisely the ones which are sent. So the coproducts in ADM are sent by this functor precisely to the weird coproducts of contramodules. Yeah, precisely. Yes. Okay. So here, this is an application to tilting theory, right? So the same situation as before, but the module is a tilting module now. And then what happens is that the heart actually becomes equivalent to the category of all contramodules over the endomorphism ring, the topological endomorphism ring. And furthermore, if we assume that T is good, so this weak assumption, which can always be achieved by some meddling, then we have, okay, so I said that this forgetful functor from contramodules to modules is not always forgetful, but this goodness property ensures that, and actually we even get fully faithfulness on the derived level. So this comparison becomes fully faithful. And then this Arham functor, which embedded this derived category over R to the derived category over S, we can describe its image. It's precisely this derived category of contramodules, which is a subcategory of the derived category of modules. So once we are allowed this topological algebra into question, we get a nice description of the image, and we get the derived equivalence between module category and a contramodule category. So this finishes the first part. Now, what is the aim of the second part? So with this in hands, now we would like to sort of merge this situation with Rickard's theorem. And this involves at least two things. So first, we would like to extend this to tilting complexes, large tilting complexes. And this will turn out to be non-trivial. So it turns out that there are pathological tilting complexes whose heart can never be a contramodule category, whatever topology we choose. So we will actually have to cook up some condition on a tilting complex, which is hopefully natural and which will make the thing work. Secondly, we would like this to become, as in Rickard's theorem, to be in a form of an equivalence. We would like to parametrize some class of derived equivalences. So hopefully the condition we cook up will be natural enough for this to be the case. Okay, so that's the second part. And I will take a few steps back and again work in a generality of compactly generated of a triangulated category. And this time I will need a compactly generated triangulated category. And I will need to talk about purity. That will be one of the main ingredients of this part. So if I got it correctly, purity in triangulated categories was discussed in the seminar some months back. So I will, which is long enough for me to be to sort of go over it again, but I will be relatively brief. So we have a compactly generated triangulated category, and this will denote this TC is the full subcategory of compacts. And how does the purity theory arise? So the first step is sort of tautological. It's more psychological, right? We consider this category of compacts as a ringoid. So that's just noticing that by definition, this is a skeletally small pre-additive category, and therefore we can consider the category of modules over it, which is by definition the category of contravariant additive functors from TC to abelian groups. And we have this comparison functor. So there is a functor from T to this module category called the restricted Yoneda functor, which essentially does what it has to, right? So it takes an object from T, we take the contravariant home functor, and then we restrict it to compacts, and we get a module here. This functor is nice, and the hope is that it will transfer problems from the triangulated category T to this module category. But it is not so easy, of course. So the problem is that this functor is not fully faithful, almost never. So it actually is almost never faithful. Usually in a triangulated category, there are maps in a large triangulated category. There are maps which are non-zero, but this is not detected by compacts. So this almost always fails to be faithful. And also quite often it can fail to be full. Nevertheless, Krause used this to develop a very useful theory of purity. There's also a parallel work of Belegianis, I should add. How does it work? So essentially, we say that a morphism in T is pure something whenever its image in this Yoneda embedding is something in the module category TC. So namely, we can define pure monomorphisms in this way and pure epimorphisms, as well as pure triangles, which are sent to exact sequences here then, so it doesn't fit perfectly, but whatever. So we have the notions of pure monomorphism and pure epimorphism in T. These are not categorical monomorphisms and epimorphisms. This would make them split, but the terminology is like that. And we can also define notions like pure injective objects and so on and so on. This will not be so important in my talk today. So this is the notion of purity. And in fact, we have a whole sort of theory. We have a whole model theory of compactly generated triangulated categories. So this has been developed by Preston and collaborators. I will need just one notion from this theory, which is the notion of definability. So we have something like first order definability in compactly generated triangulated categories. So a subcategory C of T is called definable if it is of this special form. It is defined by home vanishing, defined on some set of maps between compact objects. So there is a set of witnesses, some maps between compacts, and this category contains all object X which vanish in home F. Such categories have special properties, which I will list in a bit. In particular, though, we can define a definable closure. So given an object X, we can define def X to be the smallest definable category containing X. So this is well defined by the definition. We just look at all maps between compacts which vanish in a home functor on X, and this defines the definable closure. So this is something like the category of all objects which satisfy the same formulas as X, where formula is something defined by a map between compacts. Definable subcategories enjoy some closure properties which come from the definition. So of course they are closed under products. This is defined by home vanishing, but also since this is defined on compacts or maps between compacts, definable subcategories are closed under pure monomorphism, or rather the domains of pure monomorphism and pure epimorphisms. This also implies that this is closed under coproducts, but that can also be seen directly from the definition. And if we are a bit lucky and T has a suitable enhancement, in particular if it has a model, then actually these closure properties characterize definable subcategories. So the definable subcategories are defined by closure properties in most cases. These are results of Laking and Laking-Vittoria. Okay, so this is the purity ingredient, and now I will pass to, so I said I will define a special condition for a tilting object, and here it comes. So a tilting object will be called decent if the following condition holds. So the definable closure of T will all be contained in the tilting heart. So, okay, what does it mean? Some remarks. In particular, So this is defined for a tilting object, but it will immediately imply actually this tilting condition. This is because this definable closure contains the additive closure, and then the additive closure inside the heart. So we immediately get the tilting condition. So what we define is some special type of a tilting object satisfying something more. And it is satisfied in the Rickard setting. So any compact tilting object satisfies this. This is easy to see because if the tilting object is compact, then the heart is definable. It is defined by orthogonality conditions with respect to T. So it becomes definable automatically. And also this fits the Positselski and Šťovíček setting. So any tilting module over a ring is also decent. That boils down to the fact that if we take a definable closure of a module, it will consist of modules. It will not run away to some other degrees. And then there's no fear of creating some negative self-extensions. Okay, so the point is that this maybe a bit stretch condition makes the theory work. So in the generality of compactly generated triangulated category, such a decent tilting object, so we can take its endomorphism ring, and there's again a way how to endow with the topology. I will not write the definition here, but it's similar idea as with the finite topology. So the finite topology of a module was arose from finitely generated submodules. Here we will look at maps from compacts to T, and they will give rise to topology on the endomorphism ring. So this turns out again to be a complete ring, complete linear topological ring, and the heart is again equivalent to the category of contramodules over that. Some remarks on the proof. The proof is a cheat. So we use the Yoneda embedding to the category of modules over this ringoid, and we transfer the problem there. And then we apply the Positselski and Šťovíček result. The decent condition will make sure that this works, that first this endomorphism ring will be preserved. So this is a special case where so this condition sort of assures that the Yoneda acts fully faithfully on this. And secondly, it will transfer the compact topology to a finite topology, which is defined in this module category here. So, okay, so we have this special condition, and it works under this condition. It works by reducing into essentially to the module theoretic case. Now the question is how natural is this condition, at least in some specific setting in the derived category over a ring. And it turns out that there it can be interpreted in a natural way, in a fairly easy natural way. So let me pass to that. So now we work over a ring in the derived category of a ring. And I already mentioned this character duality functor. So to be a bit more precise, we have this Arhom functor over integers to this injective cogenerator, which goes from the derived category on the right to the derived category on the left, and also in the converse direction, of course. So this is a nice conservative functor. And the point is that it plays nice with silting theory. So if we start with the silting complex and we dualize like this, what we obtain is a cosilting complex on the left, in the derived category of left modules. So this result follows from our work with Lydia and Jerry Hegel, but it actually follows a sort of iterative process. This was known for special cases long before that. And then the result is the following. So the following are equivalent for a silting complex. So we are now in the setting of silting complexes over a ring. This silting complex is decent, so satisfies that condition, which to recall implies that it is actually tilting. And the characterization is as follows. The character dual is actually cotilting. So it is again, it will give rise to some derived equivalence. And this is natural and useful. So natural from the point of view of giving rise to Morita theory. I will explain briefly. And it is also useful because now we have a supply of examples of this. At least, for example, in commutative algebra, there is a very good supply of decent tilting complexes. So as a particular consequence, we get that if a dual of T is cotilting, then T is tilting. This is a particular consequence of this. It turns out that the converse is not true. In other words, there are indecent tilting complexes which do not satisfy this condition. And actually there are counterexamples which do a bit more. So one can construct a very pathological tilting complex, as I indicated earlier, whose heart actually cannot be a contramodule category. So even with some different choice of topology, it cannot be a contramodule category. So there are limits to the theory. I will not
Can I ask you a question about these indecent tilting complexes? Can we classify
Yes.
them?
So far there are examples. I have no ways. I actually do not. There are even some like questions whether they exist for particular classes of rings. At this point, there's a lot of questions, and I do not have many answers. What I know is there are examples of them.
Okay. Okay.
Yes. So yeah. So how does one know that some abelian category is not a contramodule category? So contramodule categories enjoy some special properties. They are not general abelian categories with projective generators. There is something categorically special about them, and it's the following property. So given a projective generator of a contramodule category, we can consider this natural map from coproduct to product over any set, and this will be a monomorphism. This is not true in any category with a projective generator, unless the direct limits are exact, of course, but this does not happen in these categories. So this is precisely what fails for that example. So that example cannot be a contramodule category. Okay, good. So the promised Morita theory result. How does it work? So there will be two results. The Rickard's Morita theory has two directions. It is an equivalence. Here I will need to be a bit more careful, so I will decompose it to two results.
Can you have a look in the chat, please?
Yes. Let me see. Can fail. So there are tilting complexes such that the heart is not a contramodule category for any complete linear topological ring. There are examples of that. It is not true that for any indecent tilting complex, at least, okay, I do not know what happens for general indecent tilting complex. It might be that there are examples where the tilting complex is indecent, but its heart is a contramodule category with respect to some different topology. This might happen as far as I know. But there are examples where it cannot happen. Yeah, there is a lot of stuff that is not known presently. Okay, so if there's no further question at this point, okay, yes. So one half of the statement is the following. So T will be a good and decent tilting complex, very nice tilting complex. So this good, as I said, okay, I didn't define it for complexes, but again, this means that the tilting complex is compact as a DG module over its DG endomorphism ring. Yeah, that's one way how to define that. And this decent, okay, we've seen that. Then we have the topological endomorphism ring with compact topology. Then what happens? So we get derived equivalences. So we already know that the heart is a contramodule category. So we get this derived equivalence now from the general theory. And actually here it again holds that it can be represented by this Arhom from T. What we also get is the left-hand side thing, but it will not be symmetric. So it will be symmetric in the topological algebra sense. So we will get a different category here. So we get the derived equivalence on the left side of our modules to the category of left S discrete modules. And again, this is represented by this tensor functor, derived tensor functor. And finally, we get, again, the compatibility with tensor structures. So here we get the derived tensor over R, and here we get the derived contra-tensor functor over the topological ring S, and this square commute. So this is this should be seen as analogous to the picture I had on the slide with Rickard's derived Morita theory. But you get these main differences, right? The contramodules and discrete modules. So that is the sort of that is one side of the picture, and then what I promised that there is a converse to this of sorts. So this actually parametrizes some class of derived equivalences, this tilting theory. So what does it say? And the statement is a bit convoluted, but okay, let's see. So in Rickard's statement, we had a couple of rings. Here we will have a ring and a topological ring, so a complete linear topological ring. And the assumption is that we have a derived equivalence. And due to the lack of symmetry, actually, I need to assume both of the derived equivalences. So the derived equivalence on the right between R modules and R contramodules. Sorry, these rings are different. I cannot, maybe not the best notation here. And also on the left. So we have the category of left R modules and the left discrete modules over this German R. Yes. And in the addition, I need to assume the tensor compatibility. So I need to assume this square for it to commute. then we get the converse. Then the statement is that there is a good and decent tilting complex. So again, the same type of data, such that its endomorphism ring together with the compact topology is topologically Morita equivalent to R. So this can be defined internally. There is a paper by Positselski and Šťovíček, a different paper than the one I cited. But what it means is the sort of expected thing. It means that the contramodule categories are equivalent and the discrete module categories are equivalent. So that is the statement. Of course, there are some natural questions to ask, I believe. So one of them would be, so okay, is it enough to assume just this equivalence, maybe, or maybe just this equivalence? The full answer is I don't know presently. I have, under some special conditions, I have a class of rings for which this is equivalent, the equivalence on the left. And I also have some conditions ensuring this, that assuming that this equivalence on the right is enough. In general, I don't know. The problem seems to lie with the sort of absence of knowledge of contramodule categories. In general, there are a lot of questions. There are a lot of module theoretic statements which we do not know how to generalize to contramodules, and it seems hard. But, well, hopefully we will know more later. Okay, so that's the end of the second section, and I can tell you a bit about the application, but it seems I'm almost out of time. So the question is now, for how long will you allow me to continue?
We started a couple of minutes late, so I think it
couple of minutes. So I will tell you some. Okay, I will tell you parts of the. I will not go through the whole last section, which will be probably too much. I will end maybe in the middle. So there are some applications of sort of different kinds. I will just cherry pick, and the ones I will talk about are in this more recent preprint with Lorenzo Martini. The applications, the first part of the applications, and it will be the only one I will talk about, again, is applicable to general ring. And then we have some further applications which specialize to commutative algebra, and this I will skip today, I think. So what is the shape of the application? So there is a lot of literature on the question of finiteness conditions of certain hearts of T-structure. So say we have a T-structure whose heart is Grothendieck, and then we can continue asking questions. We can ask whether it is locally finitely presentable. We can ask whether it is more maybe locally coherent, maybe locally Noetherian. And there are some tools for that. And this is, in a sense, addition to the tools which uses this topological machinery. So what are the finiteness conditions that I will be interested in now? So a finitely presentable Grothendieck category is called locally coherent if, by definition, the subcategory of finitely presented object is abelian. So in other words, if kernels of epimorphisms between finitely presentable objects are finitely presentable. And a slightly less usual notion, locally coperfect, under the first condition, it just says that this category of finitely presentable object is Artinian. On its own, it means that the category satisfies DCC on finitely generated objects. So in other words, a category satisfies these two conditions if and only if it is the int completion of an Artinian category, Artinian abelian category. And something very, very classical, what does this specialize to in case of module categories? So this is Chase's result from 60. For a ring, the category of left R modules satisfies these two conditions if and only if. So there is a ring theoretic characterization. This is actually where the nomenclature comes from. But more interestingly, it all boils down to property of a single module, of the regular module itself of R. So this happens if and only if R is product complete, which means that its additive closure is the same as its productive closure. So at is the same as product, as prod, which equivalently means that projective modules are closed under products. That's another way how to put it. And okay, we might be interested in a topological version, topological algebra version of that. And there is some theoretical background is set for that. So this is a different paper by Positselski and Šťovíček, which considers these precise two properties, right? So again, R is a complete left linear topological rank, that basic datum. And there is a notion of it being topologically left coherent. And that by definition really means that the category of discrete left modules is locally coherent. As far as I know, in general, there is no like topology, there are no conditions on the topological ring itself which are known to encapture this. So this is the definition. And there is a notion of being topologically right perfect. Again, this generalized the ring theoretic notion. So it says something about topological Jacobson radical. The topological quotient should be topological semi-simple and so on and so on. There is this like topological version of the module theoretic results which are classical. And this implies that the category of discrete modules has this second property. So it is locally coperfect. Actually, it is not known whether this is an equivalence. This is known as the topological Bass theorem. So topological version of the classical theorem of Bass, the theorem P. It is not known in general. This seems like a hard problem, but it is known if the ring is already topologically left coherent. This is one of the results of this paper, one of the main results. So back to our tilting setting, we have what we proved is a Chase's theorem in this setting, so in this particular topological setting. So again, T is this descent tilting complex. See, it's a dual cotilting complex, and we have the topological endomorphism ring. What is the result? So the cotilting heart, which we already know is equivalent to the category of discrete modules over the topological endomorphism ring of T, has these two properties. So it is the incompletion of Artinian category, in other words. So it is locally coherent and the category of finitely presentable object is Artinian. This is equivalent, okay, to these two topological algebra conditions. But mainly, this all is captured by the object T, by its special property. So this product completeness, meaning that prot is equal to at. And this turns out to be useful. So we have examples coming from commutative algebra where we have applications of this large tilting theory where we couldn't prove the local coherence of the heart otherwise, and this topological technique worked. So we have an example of this T, actually a source of example of this T where this condition was good to check. Okay, so I think I will put no further comments. I will skip the commutative algebra section, which is probably for the best. So thank you for your attention.
Thank you very much, Michal. Let us all unmute ourselves and give the speaker a round of applause. People are clapping online. Any questions, anyone?
A question, Michal. You mentioned this result of Silvana, Alberto Tonolo, and Francesca Montese. I think in that paper they describe the image as a localization in some way. So how does this relate to contramodules, their description?
Yes. This is something I sort of didn't comment on, but actually, so this fully faithful functor actually fits into Recalman. Mm-hmm. So in particular, it has, as you said, it's a localization functor. It has a left adjoint, and that left adjoint has another left adjoint. Mm-hmm. So in that way, it fits into Recalman. And well, what this contramodule interpretation does, so now here we also have this Recalman between so in the special setting where this is fully faithful, we actually have a Recalman which compares the category of S contramodules and S modules. There is a Recalman connecting mm-hmm. those two.
Okay, so it's more about the functors, the original description, than the category itself. Yeah. Okay.
Yeah.
Mm-hmm. Thank you.
Okay, Jan. Any other questions or comments? Am I audible, by the way? Can you hear me?
I can hear you.
Okay. I had three very... Okay, sorry. There is a question from Victor Carmona in the chat. Is that more or less the connection of contramodes with protortion modes?
No, I think that not in general. I think the connection in general is not as strong as for abelian groups. So there are some special settings where the connection is stronger. So, for example, if we take a local complete Noetherian rings, then actually Leonid Positselski has a series of paper on what the contramodules are there. They actually coincide with what is called in commutative algebra was called L0 complete modules, and well, these. So in these like small examples, they coincide with reduced cotortion modules. In the bigger ones, they do not, but that's closer in spirit to that. But in general, I don't think there's such a strong connection.
Okay. Yeah, thank you. Yeah, I had three very small questions. I'll just ask them together. You can answer them as you wish. So you said, so question number one is, what's a candidate property that you do not know? I mean, about which you don't know whether it will translate from modules to contramodules. So number one. Number two, if you go to the very last theorem, well, the last theorem that you ended with, where T was this decent tilting complex.
Well,
Yeah, the
something.
chase.
The chase one. Okay. Yeah. Yes.
So the failure of this chase result. Is the failure very noticeable or very detectable when T is indecent? That is question number two. And question number three was the third equivalent condition here. You need coherent on the left side and topologically perfect on the right side?
Yeah.
What's the motivation?
Okay, so I think I will start from the end. So from the end, I can already go to this classical ring theoretic setting. So for a ring, that's also why this go is before the perfect. So the right perfect ring is this is a ring theoretic characterization, or ring theoretic definition rather, but the characterization which comes from Bas theorem P is that you have the DCC on the left of the ring, on finitely generated ideals. So this property has one characterization on the right on the ring and another equivalent one on the left. And it actually for the module category, it has an implication, or rather, so it describes a property of the left module category, even though as a ring theoretic notion, it is more from the right. So that's the reason for that. Now, I forgot already what the second question was, sorry. Indecent, yeah. Okay, so this does not say anything about the indecent setting, and like studying these properties in the indecent setting, I don't know actually what to. I have no input there. It's out of the reach of this theorem, at least in general, due to that example where we know that the hearts in questions are not described in the lens of the topological endomorphism ring. So yeah, here I do not have any answer at all. And the first one?
So there might be, you sort of implied that there might be module theoretic properties that don't translate well from modules to contramodules. So what could be a candidate example of such a property?
So there are certainly more. So for example, some of them have been studied. So for example, there is this Lazard-Govorov theorem, which says that any flat module is a direct limit of finitely generated projectives, and there are counterexamples to that in contramodules. This does not always hold. That there is a notion of flat contramodule, which is also sort of relevant to this picture. And it is known that this analog of this theorem can fail, and it holds sometimes. So there are things which were interesting to Leonid Positselski and were studied. And from my point of view, which is sort of relevant to this question about this Morita theory, so it seems that if we want to start with just this derived equivalence and ask whether we can recover this whole picture from that, it seems that one is led to study ultraproducts in the category of contramodules, the ultraproduct construction. So in the category we have products, coproducts. There are direct limits. They are not exact, but anyway, we can talk about what an ultraproduct should be. And it seems that this question is connected with some properties of ultraproducts. So there was this another thing I mentioned is that this morphism is always monic for contramodules for the projective generator. One may replace this by something like embedding of a reduced product into product, something more general than coproduct, but some direct limits of the reduced product, which is indexed by some filter. And it is not known for that, whether this is always a monomorphism. So that's a very sort of module theoretic question, which is extended to contramodules, which is not known, and which would actually help solve this question. But one can come up with many questions which seem to be hard to transfer to contramodules. Maybe one remark which is sort of more useful is that a lot of times things become easier if the topology has some properties. For example, if the topology has countable base, that's maybe connected to one question which were earlier. If the topology has countable base, then a lot of stuff happens to become easier. For example, it is then possible to, if there's a countable base of two-sided ideals, then this topological Base theorem P has a proof.
I think also then the Lazar-Govorov holds, yeah? Is that correct?
I think so, yes. I think so.
Yeah, that's very good to know. Any other questions, anyone?
There's a question about the slides. I will very happily provide them. Maybe it will be easiest if you send me an email. Or maybe or if there's some place where it can be put, then I will happily provide them. Okay.
Announcement. Okay, if there are no more questions, let us thank our speaker once again. Okay, yeah, thank you all for coming. We have Arun Baya from Edinburgh speaking next week. The talk will be on Wednesday, not Thursday, because there might be stuff at an airport on Thursday. Thank you all for coming.